not an easy. All right. We are going to talk about, there's actually, this section is really heavy with stuff, and so my idea is to break this up to two different lectures. The first part will focus on arc length and curvature, and then the next part will focus on a Frenet frame, a frame that we would create as we move along a space curve, as we move along a curve. And they're related, of course, and they're related to the motion stuff that we've been talking about. And one of the big ideas there is the unit tangent vector, which we've already defined and discussed. So for today, let's start by talking about arc length. And we have seen arc length formulas. In fact, we saw an important arc length formula in Chapter 10, where we're talking about parameterized equations, parametric equations. and we found a formula for that. And so we're really just going to base it off of that. So, but we'll look at it from a vector point of view and see if we can make our notation a little bit more compact. So remember that we have our R of t, and let's put this in three-dimensional space. But let's also remember that we can always fall back to 2D if we need to. And also remember that we can extend this to 4 or 5 dimensions or higher dimensions if we wanted to. But again, for the sake of visualizing it, we'll stick with 2 and 3 dimensions. So our R takes a real number and sends it to R3. So we're talking about a vector valued function. So I'll do a little recall here where we recall our formula for parametric equations, x of t, x equals x of t, y equals y of t, that the arc length is defined, if they call it L, whatever they call it, yeah. So it's going to be the square root of the derivatives squared So this is our old arc length formula. And if we look at how this is set up or how it's designed, and then if we look at what we're dealing with now in R3, we can imagine what the formula should look like, right? And so let's jump to that idea for this vector function. Our arc length is going to be given by, again, depending on if we want to go from what to what, your limits will be based on your t. And then this looks like it will be just the square root of all these things, x prime of t squared plus y prime of t squared, and then we just throw on that last one. Okay? So, for today, for this section, we'll use the S. And that there's actually a reason for that. All right, so that's the easy part, right? Easy. Okay, now let's focus on the integrand, just stare at it, and see if you can extract vectors out of this. You understand what I'm saying? No. Look at it, and then at some point somebody's going to say, hey, that looks familiar, or hey, we can rewrite that as something. It's the magnitude. It's r prime of t, and it's the magnitude of that. Yes. Have we done that before? So, in physics? So really, if we took the derivative and square each component and then put it all, add them up, put it all under square root, that's just the magnitude. Or the derivative of the components is just the velocity vector r prime of t. And then if you square each one, add them up, and then put under square root, it's just the magnitude. So here is our first important piece of information or formula.
That's why you're calling it S, is that's speed and Arclength, so it's like a double S situation.
No. Let's do a couple of easy examples. I hope they're easy. Let's see. It's always not easy when I make stuff up off the top of my head. Let's go really. Oh, by the way, if we look at this formula, right, and this formula was kind of set up for a three-dimensional space curve, it actually will work for 2 dimensions as well. If we look at a two-dimensional function, two-dimensional vector valued function, it just has an x and y component. And then here you have x prime, y prime squared, and stuff like that. So it's really just the same as r magnitude of r prime squared, right? All right. So a couple of simple examples. Let's do a circle in 2 dimensions. So let's say your r of t is equal to let's give a radius here of 5. And we'll go from, I don't know, 0 to 5. Let's go all the way around. So this is our r, and we got our limits from 0 to 2 pi. So let's find the arc length of this thing. So the arc length is going to be, according to the formula, we need r prime, which is derivative cosine is negative sine, right? And then we want the magnitude of that. So we got 25 sine squared t plus 25 cosine squared t. And, well, look, that's just equal to 5 square root of 25, right?
Oh, yeah.
So, this happens to be a nice example. And like I said, they're not always going to be nice examples. And so when you do your homework, you'll see that, type your answer to 3 decimal places or whatever, because you'll just have to take your integral, put it into Wolfram Alpha or your calculators, and then find some approximation. All right, we have your 8. Yeah.
So 5 is not the arc length of a circle, though.
No, because we haven't finished this. This is just what goes inside of the integral, right?
Oh,
and
yeah.
and so the actual arc length now.
Knew that.
So the actual arc length now is your
Oh, yeah.
integral from 0 to 2 pi of the absolute value or the magnitude of r prime, which we computed to be 5 dt. And so then this is just 5 times t from 0 to 2 pi, which is going to be 10 pi. And that is the circumference of a circle radius 5. Okay? So is that okay? Does that make sense? All right, let's do another easy one. I don't wonder if we should do another easy one.
Solve all these things with these squares and their square root because trig substitution is not.
Yeah, you punch it in your calculator. Right? I mean, I haven't decided yet. Let's do another easy one. This time let's go to 3 dimensions. We can still go from 0 to pi. And then we do the same thing that we did. And again, this is easy because there's these nice sine and cosine functions that would, when you square them, you'll use that identity, and then everything will look nice and easy. Otherwise, you'd just be using the calculator. So we have negative sine t, cosine t, and 1 for your derivative, and so the magnitude should equal to sine squared t plus cosine squared t plus 1. And I think that's just the square root of 2. And then your arc length is going to be integral from a to b of the magnitude of r prime dt, which is just going to be, again, square root of 2 times t from 0 to pi. Okay, if you have anything else aside from these trig functions, like some things with t's, and so you'll have square roots of something squared. If you're doing it by hand, you may need to pull out your old trig substitution techniques and things like that. But I'm not teaching that, so I'm not going to worry about doing stuff like that. So this is arc length. Is that cool? Yeah, what?
There's on number 4 in the homework, there's a variation of it that I couldn't understand.
In this section, 13.3?
You're using the they give you like parameterized equations.
Yeah. All right, well, if we have time, we'll take a look at it. Okay, let's take a look at a couple of parameterizations. Let's talk about parameterizations in general. What does it mean to parameterize something? And this might relate back to the quiz that you guys had. Quiz number 1, I think, maybe. So let's parameterize a circle of radius 2 with radius 2 of. And if we keep this simple in 2 dimensions, we can say our parameterization might look like this. X is equal to cosine t, y is equal to sine t. 2 in the front, thank you. And then if we were to be responsible with our parameterization, we should also say what the limits are for this circle. And so we can say that the circle is being drawn out from 0 to 2 pi. Right? And then for the quiz that I gave you guys back in the first quiz number 1, I think I asked you to parameterize the same circle, but I wanted you to finish parameterization from 0 to 2 pi, or from 0 to 1. So if your limits now go from 0 to 1, what did you have to do to answer this question correctly? Change the period. And so what did the period change to, you remember? 2 pi t. That's a 2 pi in there. Somebody's going to look at these notes later on and say, what? All right. What's the point in this? Well, the idea is that if these 2 different parameterizations parameterize the same thing, then our arc length should be the same if we use these things with the same limits. Does that make sense? So what we're saying is that your S should be the same for either way, whether you're doing this derivative from 0 to 2 pi of whatever goes in there, or you integrate this from 0 to 1 of the stuff that goes in there, that they should be equal to. And what should this equal to? What's the circumference of the circle radius to? 4 pi? So your answer should be 4 pi for either of these parameterizations, right? Should we go through this work? Take the derivative, square it. So the derivative of this is 2 sine t squared plus 2 cosine t squared. So it looks like there's a 4 in there. So take it out, it becomes a 2 from 0 to 2 pi. So that turns out to be 4 pi. So that checks to 4 pi. And then if we were to take this integral, the derivative of this is 2 times the derivative of the inside 2, right? So that's 4 pi sine t squared plus 4 pi cosine t squared. And so this integral would be the 4 pi squareds would factor out, and then the square root would take away the square, so this is just 4 pi dt, and that's just equal to 4 pi. So it's the same, which is what we should expect, right? Yeah?
Why do not have the 2 pi on the inside and do the chain rule?
Oh, because I forgot. You know what I mean, right? I already made this look pretty, so you know what I mean. Anyways, like the sine t, cosine t squared, all that stuff goes away, and you get 4 pi. So the main gist here is that different parameterizations will give us different arc length, or will give us different velocity vectors. But if you're looking at the arc length, your parameterization will have different limits, and so we'll eventually get the same arc length. Which better work, right? So let's go back to the idea of the parameterization. So there's different ways to parameterize things. And so it turns out that there's this one way to parameterize things that's really interesting and can make some of our formulas look a little bit simpler if we can do this. If we can do this. And the way to think about a new parameterization is to parameterize it so that, how should we do this? Let me see if a picture will help in figuring this out. I have a couple of circles that I parameterized. One I parameterized using regular parameterization, and then the other one I parameterized using a different kind of technique. And what I want you to do is this is to focus on this value over here. I don't know if you guys can see that. That's your t value. We'll call it a parameter value, your t value. And as I'm drawing this out, I'm measuring the arc length from the beginning. And that beginning is when t is equal to 0. Okay? This graph is going to measure the arc length as I move my parameter. And then this graph is also going to measure the arc length as I move this parameter. So I'm going to start moving the parameter to draw out the circle and at the same time measure the arc length. So you can see the graph on the left side goes a lot faster than the graph on the right side. Does anybody see anything interesting happening here? Say it again? Say it. 25% of this one? Okay. It looks like it. Let's see. Let's go a little bit further. And it looks like the graph on the left is going to draw out over itself again, but it'll still compute the arc length, right? There are different parameterizations, kind of like the two parameterizations that we had. But is there anything else that you noticed? Remember, you're supposed to be looking at like 3 things. What? The arc length for this one is the same as the t value for this one, right? Is that right? So it's hard to see the numbers, yeah. Okay, the number here for the t value, it's hard to see that number. It's 9.1816, and the arc length for this is 9.816. And the arc length for this one is 45, so that's really big. But what I have here is whatever this parameterization is on the right side, it looks like it's the same length as my parameter whatever my parameter is gives the same length as the arc length. Whatever the parameter is, yeah. And so that's your length. So if you integrate with respect to this special parameterization, your top limit is going to end up being the actual arc length. Okay? All right, so does that concept make sense? And if it doesn't, can you ask a question? That's usually the hard part, right? It's so far beyond what's happening and that I can't even come up with a question. Yeah?
So what does the equation of that circle look like?
This is a circle of radius 5. The parameterization on the left side is our standard parameterization. Our parameterization on the right side, which is the one that's parameterized by this special parameterization, is given by 5 cosine t over 5. So what we're doing essentially there is we're extending our period, our cyclic period, so that it's going to measure the actual arc length as we go along that particular parameterization. Yeah.
You just rearranged s equals theta r, right? And your parameter is theta. And so so basically what you stuck in there was s over your radius. So that's how you got it to be the same, right?
For circles. Yes. Tried to tell the students to do their posters lengthwise. And so if they do it sideways, then only half of it sticks. That's what that's about. Anyways, all right. But I want to know if you get the idea of this special parameterization. How to find it is a different story. We can find it easily for circles, and for everything else, it's not so easy. Okay, so how to find this parameterization is not the issue. What I want is to know is, do you understand? Caesar actually said it best when he said, it looks like, well, maybe I should just write it down. The idea behind this special parameterization, I keep calling it special parameterization. Why don't I just say what it is? This is called parameterize by arc length. So this special parameterization is called parametrizing it by arc length. Okay, and what that means is that your R, let's call it R, I don't know what to call it. I want to say R sub 0, R sub A. And I'm going to use S. Actually, it doesn't matter what I use. Let's use T. So R sub A of T is parameterized by arc length. If if something, I can't remember what. I think it's integral from a to s. This is kind of shaky here. Oh, that a. I know I shouldn't have used a. Let's put a dot there. So it's parameterized by arc length if this top limit over here is actually the arc length, measuring the arc length as you go along this parameterization. Okay? And then in terms of notation, a lot of times they just write this when R is parameterized by arc length. We write R of S. Because S is the arc length, and we're saying we're parameterizing it and using S as the parameter. Okay? What? Yeah. So we'll do the circle as an example. Again, it's easy to deal with. Yes?
Does the book use that?
I don't know.
It uses something
All right, let's see if we can do an example. So should we? I guess we should do this one. See if we can parameterize this by arc length. Circle a radius 2. Let's try to parameterize this by arc length. So far we have this idea of a parameterization for the circle. X equals 2 cosine t, y equals 2 sine t. And if we go from 0 to 2 pi, and we have the whole circle. So we computed the well, we didn't really find this. We kind of skipped over the step, but let's figure out what the tangent vector is. The tangent vector is negative 2 sine t to cosine t, and then the magnitude of that is equal to square root of 4 sine squared t plus 4 cosine squared t, which ends up being 2, right? So if we were to we're interested in finding the arc length. Don't write this down yet if you guys are taking notes, because I'm going to change things around in this equation. We're starting at 0. We're going to 2 pi, and then we have 2 dt, right? So here's where I'm going to change it. Instead of going from, I want this s, I want to describe this s as a function of t, and I want this t to be up here, which means I have to change the t's in here and use a dummy variable. So any variable that's not s or t, like a u substitution or something. All right. So what we essentially did was to make this as a function of t. So s is a function of t. And then I'm going to find a relationship between the generic parameterization variable t that I have versus the actual parameterization of s that I want. And then, so if I solve for this integral, now you can write it down if you are taking notes or whatever. If we solve for this integral, let me rewrite it as 0 to t of 2 du. This is the integral of 2 du is 2u, and I want to evaluate this from 0 to t. And so I'll put t is equal to, u is equal to t, and then u is equal to 0. So I'll have 2t. So my s parameter, my s of t, is equal to 2t. And so what I really want to do is replace my t parameter with something with an s in there, right? So it'll be s over 2. So t is equal to s over 2, and then now this, I'll replace my t, what used to be a t. So I have x equals 2 cosine t, and instead of a t, I'm going to replace it with s. So y is equal to 2 sine t, but instead of a t, I'm going to replace it with s over 2. What's that give me? That gives me my r dot. It used to be an a, but I covered it up as not a t, but an s now. And that's equal to your x component, comma, your y component. And then that's your parameterization by arc length. So now, if I integrate this, or if I want to find the arc length where my s value goes from 0 to 5, then my arc length is going to be 5. Without having to do this, if I want the arc length from s equals 0 to s equals 5, then arc length is going to be 5. Okay? So that's how to parameterize by arc length. Is that cool? Again, in practice, you won't be parameterizing by arc length unless there's a special exercise where somebody asks you to parameterize this by arc length. But if it's going to be an exercise that should be doable, it would be like a circle or maybe even a helix, because anything beyond that would be kind of difficult to parameterize by arc length. It could be done, I think, but you'll have some weird integral things because of this relationship that you're trying to get. Your integral, if we're dealing with circles and helices, then your magnitude of your velocity vector is constant, and so that makes a nice, easy integral to work with. But if you have something else that's not constant, especially with the square root business over here, That's going to be a lot more difficult to deal with. All right? Is that idea okay? Parameterizing by arc length? All right.
So is it possible if we got as a t integral from 0 to t to du, that we would just stop there and just know that it's going to be over 2?
If this is constant, yeah.
Yeah, that's what I'm saying.
Yeah.
If it had variable, we could do that with this constant.
Yeah. So if it's a variable, then hopefully it's a linear thing that you can solve for. But otherwise, if it's like, if your answer here happens to be, 2t squared plus 5t or some quadratic or some exponential or something like that, then solving for t might be a little bit more difficult. All right. Let's move on. All right, let's move on. Let's go to our next topic. And we will use the idea here of something that's parameterized by arc length, and we'll just start to get used to if we're going to parameterize it by arc length, we'll call it S. All right. Our next topic is we're dealing with vector-valued functions, which draws out in 2 or 3 dimensions, draws out curves. And if you have a curve, whether you're looking at this as a curve in space or a curve on a plane, there are some points in a curve that's interesting to look at and to read and try to get some ideas about. Like if I look at this piece of the curve over here, it looks kind of like a straight line, right? And if you look at this piece of the curve over here, it looks like it's bending a lot. So in geometry, it sometimes would be important to try to measure how something is curving. And so the measure of how something is curving is called curvature. So that's what we're going to take a look at, curvature. How are we going to take a look at that? Oh, I need the formulas. Is that the first formula that they have? So formula for curvature, let me just give you the formula for curvature. And in most books they use the Greek letter kappa, which is essentially K. But it's Greek and it's kappa. And what does this equal to? Oh, that formula. All right. Well, where does this formula come from? Remember what big T was? The unit tangent. So big T is a vector, and that vector is the derivative of the position divided by the derivative of the position divided by the magnitude of that same thing. That's T. And just to get like a visual argument here, which is nowhere near a proof, if we look at, because this is a unit vector, the length doesn't matter, so what's going to matter is the direction, how the direction is changing with respect to t. And if you look at this first thing that I highlighted, if I move around that point and find the direction vectors, the unit tangent vectors near that point, they're fairly going to be straight and they're not going to be changing much, right? But if I go over here and I take two unit tangent vectors that are close to each other, there is going to be a big difference in their directions. So if we focus on the unit tangent vector and see how the direction changes, the bigger the change, the more curvature there's going to be. So that kind of makes sense, doesn't it? That idea makes sense. So that's what this is. It's the unit tangent vector with respect to the S. What's S? That's the parameterization by Arclength that we just talked about, right? So using S as a variable, an independent variable for us is kind of strange because we just had talked about it. But what is S equal to again? Do you remember what that one? It's the magnitude of r prime of t dt from A to B. Or if we want to keep it as a general integral, I'm just going to cheat a little bit and take away A, B. Generally, that's what the arc length is, right? Okay. So from this formula, by the way, it's absolute value? Or?
Yes.
Yeah. So whether you're curving to the left or to the right, well, if you're in 2 dimensions, if you're following this path, when you curve to the left and curve to the right, you can kind of assign a positive or negative to that. But when you're in space, there's no more left or right, right? If you look at the roller coaster, if you're in a roller coaster and you see how it curves and stuff, it kind of, you get twisted around, so your idea of left and right might change. So I think when they start measuring curvature, they just want the positive value, like a speed or something like that. Anyways, the idea here is that both capital T and S look like there might be functions of little t. And so what we might be able to do is for us to be able to compute this in some way, form, we can write dt over d little t divided by ds over d little t, like a chain rule type of thing. And now at least I could take the derivative of each of these things and it would kind of make sense. Oh boy, what's the derivative of the t with respect to t? The derivative of this thing with respect to t. Since they both have t's, would the quotient rule do? What? No, because it's still a function of t. So if you want to look at it this way, the denominator is a scalar and the numerator is a vector. Okay, so it looks like we can think about this as it's still going to be a complicated product rule thing. All right, well, there's another formula in the book.
Oh, it is capital T is the absolute value of r prime of t cross r double prime of t. And absolute value divided by the absolute value of r prime of t cubed. I don't know if that's what you're looking for.
Yeah.
Okay.
Well, let's just say there was some magic that happened.
There's magic I have in the book because it just looked to that.
And the proof is underneath that, so it says.
So yeah, so there are rules for taking derivatives of quotients or products of functions and stuff. By the way, the derivative of s with respect to t uses the fundamental theorem of calculus, so that's just the magnitude. It's just if you're taking the derivative of an integral, it's just going to be whatever is inside. So that has an r prime of t in the denominator, and then by doing this chain rule, quotient rule business, there's going to be an r prime squared, and then somehow the top gets reduced or gets simplified to look like this thing. Okay, so let's not worry about how to get that. Let's just say this is our formula for finding the curvature. What? Well, trust the book because it's in the book. Okay, so the easiest example of a curvature, again, is a circle. So let's take a look at a circle and find the curvature of a circle. Okay, so let's remember this formula, or at least have it written down in front of you. Yeah, well, when you cross two vectors, you get a vector. So technically, this is a magnitude, and then this thing is a vector. So technically, this is another magnitude. So they're both magnitudes, but remember that magnitudes and absolute values are the same thing. The magnitude of a scalar is just like the absolute value of a scalar. So, circles. Let's use our standard circle that we've been dealing with. And technically, when you're doing this, you want to evaluate this at a particular value. But we'll see for this case that for a circle, that it turns out that the curvature is going to be the same at every point in that circle. All right, so it looks like we have our r function, we need our r prime, and we even need the double prime. So the derivative of the x is -2 sine t, derivative of the y is 2 cosine t. Now we want the second derivative, -2 cosine t, and then -2 sine t. So they're both negative. We're going to want we're going to want a cross product of this. So r prime cross r double prime is going to be, oh wait, this is 2 dimensions. Is that a problem? Nah. If it's in 2 dimensions, then we can bring it up to the 3rd dimension just by taking the cross product. So let's take a look at this. I was just going to do it without doing the matrix, but I think it's good to see what happens when you have something 2D crossed. And if you were to cross that, if we put this on the xy plane, this is a -2 sine t, 2 cosine t, and then this is going to be, your third component is going to be 0. -2 cosine t minus 2 sine t, and your third component is going to be 0. So look what happens when you cross this. If you take a look at the I component, you cross out the I, and then you have 0 minus 0. If you take a look at the j component, you have 0 minus 0 again. And then if you take a look at the k component, then you have this business. So that's negative and negative. It's positive for sine squared t, and then minus a negative for cosine squared t, and that's in the k component. So essentially what you have here is you have a vector that's only in the k component. Now, does that make sense? Yeah, because the other two vectors are flat on the xy plane, and so your cross product, which is perpendicular to them, has to be just going up in the k component. All right, and this could be simplified to 0, 0, 4. Is that right? So that's your R prime cross R double prime. And then if we want to find the magnitude of that, I think that's just equal to 4, right? So that's our numerator. Now, in most cases, again, the circle is a special case. In most cases, you'll have this as a function of t. It means there will be a t in there. And then that's when you put in your t value. But in the case of a circle, it's going to be the same curvature wherever you are at that point. All right, now let's find the magnitude of r prime, which is our denominator. And so the magnitude of r prime is just the square root of minus 2 sine t squared plus 2 cosine t squared. And here you have 4 sine squared plus 4 sine, so that's equal to 2. And that's our denominator. Oh, we have to cube it. So your kappa of t, your curvature, is equal to the numerator, which is 4, and then the denominator, which is 2, and then this is raised to the third power. It's 8, is that right? Just 1/2.
What does that mean in terms of the circle curving away from 1/2?
The measure of curvature radius, circular radius 2 is 1/2.
So then, what is like the positive numbers of curvature? Like, is it from 0 to 1?
It could be 0 to infinity. Well, yeah, the curvature, we're taking magnitudes of it, so it's always positive. An infinite curvature? Well, I guess you won't necessarily go to infinity. Hairpin turn? A hairpin turn?
Yeah.
So technically, you know, when I say 0 to infinity, it's not including infinity. But it does include 0. Let's talk about those special cases. Well, let's talk about a circle first.
0
Yeah. So we did it for circle of radius 2, but we probably should have done it with our circle of radius A being arbitrary. But the idea here is that if you have circle of radius A, the curvature is going to be 1 over A. It's the reciprocal of the radius. So we got circle of radius 2, and we got this curvature to be 1/2, and that's not a coincidence. It actually is. What was that? Yeah, so the bigger the circle, the less it turns. All right, a line has curvature 0. Okay? So those are only two special cases. So a circle has curvature 1 over its radius, right? So it turns out that if you have any other point that you're dealing with, let's say you have some other curve, and this would be kind of interesting to look at. So if we have something similar to what we had earlier, if we take a look at a piece of this curve, at some point over here where that piece of a curve looks a lot like a line, you'll probably have a curvature of 0 for those places where it looks like it's a line. And now this is the cool part, is that if we take a look at something that has a curvature, let's say this has a curvature of I'm trying to find a variable, but if I use A, it's going to throw things off. Curvature of alpha. If this has a curvature of alpha, wait. A curvature of 1 over A means that a circle of radius A will fit it, right? So if I had a curvature of alpha, then there should be a circle of radius 1 over alpha that would fit it. Well, it turns out that if you were to draw a tangent circle, a circle tangent to that curve, the best circle that would fit that tangent to the curve will have radius 1 over alpha. That says alpha there. That has radius 1 over alpha. So that is, we can call it a tangent circle. Sometimes it's called an tangent circle. I don't know if it's called. I was going to use this word, but I don't know if it's the right word. So maybe I shouldn't use it. Okay. Sometimes, maybe I should pause the video. It's okay. I've said a bunch of wrong things in class anyways. Sometimes it's called an osculating circle. Not oscillating, osculating. So it's a circle that follows this that extends to, so imagine a curvature of 0. 1 over 0 is infinity, right? You can imagine this as having a tangent circle that has radius of infinity. Strange. But as you go further away, your circles are going to reduce with respect to the reciprocal of the curvature. And so you come over here, this will have a curvature of beta that's bigger than alpha or less than alpha, so you'll have a circle that's bigger. Because it's the reciprocal of the curvature.
Just do another extra credit where you can like draw the circle and line it with like an increasing and decreasing circles, and just slide it and see the as you go along the curve. Just saying. I feel like I can do that.
All right.
You're creating your own extra credit.
Before you guys go, I want to remind you that I had put a forum for people that are interested in sharing some graphing programs. And if nobody else shares graphing programs, at least I have a graphing program here. It's an online access to what's called a 3D plotter, which draws out a lot of different things, including surfaces that we're going to talk about after or right before the test, and then all these curves that we've been discussing. You can draw them all in 3 dimensions. So I might shift to using this because it's free, and then you guys can use it too. So you guys could take it. Yeah, you need Java in your thing. All right. See you guys tomorrow. Oh, wait, one more thing. There's a quiz online. I didn't want to have the quiz in class, so there's an online quiz. I'll put it in the announcements, but in WebAssign, Monday? All right, so it's due whenever it says it's due there. I thought it was due this week. All right, see you guys next time.